Jason Bell, and he is going to speak to us about Lie complexity of words.
Okay, so thank you very much for the invitation. So I'd like to talk about some work I did with Jeff Shalit. And the motivating problem, this was something Jeff mentioned to me, I think years ago maybe, and there has been some work on this in the past, is we're looking at a finite alphabet. And well, for this talk, we're going to let this notation fac W denote the set of factors of our word. And the question was, you know, the words sometimes have the property that some factors appear to arbitrarily high powers inside the word. And, you know, other times, you know, maybe only the square or maybe not even the square appears as a subword. So this was the question. In particular, the motivating question was for automatic words. It seemed that there were only finitely many primitive factors with this property. And we gave maybe not the sort of the most straightforward solution, but we want to look at this. And I'll introduce some concepts because I think they're kind of interesting. It's possible they've been. We're going to introduce some invariants, and I say new, but I think probably some of them are well studied or have been looked at in the past. But I think the Lie complexity function at least is new. And they're really motivated from things in algebra. And, you know, I mean, people like Christoph, you know, imported a lot of algebraic techniques in the theory of combinatorics on words. So there's some inspiration there. So given two right infinite words, we're just going to put an equivalence on these sets of words if their factor sets agree. So it's a very coarse equivalence. So for instance, if you have a recurrent word or a uniformly recurrent word, a word where the factors recur infinitely often, then you can truncate, you can remove a prefix and it will still be equivalent to W prime, where W is this, and W prime is where you remove a prefix. If the word is recurrent or uniformly recurrent, you know, you'll always get an equivalence like this. So it's a very coarse equivalence, but we're going to look at this. And I'll just, for the purposes of this talk, I'll just recall some of the basic definitions. So a word is periodic if it's of the form b to the omega, so it repeats every, you know, there's some n such that when you go n to the right, you're the same letter as you were n before. And the word is recurrent if you take any factor, it's going to occur infinitely often in your word. And it's uniformly recurrent if for every factor you can find a block and a length n, so that every block of length n contains a copy of this factor. So that's the three concepts. Probably people are aware of these, but I'll just give them just in case. And then I'll just say, this is just a basic fact. It's not hard, and I think it's well known, is that if W and W prime are equivalent, right, infinite words, then you've got the following facts: that being recurrent is equivalent, uniformly recurrent is preserved under this equivalence, and being periodic is preserved under this equivalence. So this is nothing new. I'm just showing that the equivalence sort of captures a lot of the interesting properties that we're interested in. And now we're going to put in equivalence, a partial order on our equivalence classes. So if we have two words, W1 and W2, then if the set of factors of W1 is bigger than the set of factors of W2, so every factor of W2 is also a factor of W1, then we're going to say that W1 is less than or equal to W2. And this is a well-defined partial order, and this is nothing really deep. I mean, people who sort of, you know about ideals, you'll see that there's an ideal in a certain monomial algebra, and this is just sort of that Posset order on the set of monomials. So it's nothing too bad. And so now I would like to get at the objects that we're going to look at this talk. So we're going to define some spectra. So the total spectrum is just going to be all equivalence classes of words, V, that are bigger than or equal to W. So these are all words, equivalence classes of words, where the set of factors of V is a subset of the set of factors of W. So that's called the total spectrum. And remember, we showed that these properties of being recurrent and being uniformly recurrent and being periodic are all preserved under these equivalence classes. So we can make sense and we can refine, and we can even take the subset of recurrent words that have the property that the factor sets are contained, and we get a subset of the total spectrum. And then we can make the uniformly recurrent spectrum, which is the uniformly recurrent words with this property, and the periodic spectrum. And the only thing that's interesting to note is that every periodic word is uniformly recurrent, and every uniformly recurrent word is, of course, recurrent, and every recurrent word is a word. So we get a containment that this object is contained in this, and this object is contained in this, and this object is contained in this. So nothing too bad so far, I hope. And I've just said that we have these containments. And they all inherit this Posset structure, right? The set of equivalence classes, which is tote, has this partial order, and it restricts to a partial order on these. So these are all Possets. And a question we're going to be interested in is, what are these Possets? So what we'll see is that in the case of words of linear factor complexity, they actually have a fairly nice description. So that's where we're going to go. And to understand, we're going to try, one of the big parts is to understand this. And here we're going to introduce something called the Lie complexity function. And I'll just give a quick example so you can see. Here's a word where we have X, Y, 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 Y. And you can see that the set of right infinite words that have all of these as factors, every factor of this word is either X to the Y or of the form Y to the I. So the total spectrum is just these two classes. And you'll notice that this one is periodic and uniformly recurrent and recurrent, and this one is none of the above. So in this case, the periodic spectrum, the uniformly recurrent spectrum, and the recurrent spectrum are all just one element, and the total spectrum is two elements. And another example is the two amorphs word, which we all know. And we know this is uniformly recurrent. And so what you can show is that the recurrent, uniformly recurrent, and total spectrum are all just the class of the two amorphs word. And the periodic spectrum is empty because this is a cube-free word, so it can't have any cubic factors. So, and one thing that's just basically Zorn's lemma is that while the periodic spectrum we saw can be empty, so this is, for example, in the two amorphs word, the uniformly recurrent spectrum is never empty. And this is just, like I said, this is just Zorn's lemma. People probably know this, this is not a hard thing, but people know that this theorem of Furstenberg that says if you have a right infinite word, then there's always a uniformly recurrent right infinite word whose factor set is contained in the set of factors of W. So we always get something in UREC W. And I think experts will know about this. So in this, it's not new, but I think it's just worth pointing out that we do have this topology on the set. So I'll just give an overview. So just in case people haven't taken topology for a long time, a topology for us, we're going to think of it in terms of closed sets rather than open sets. And in that case, you want the empty set and your ambient set to be closed. and you want it to be closed under finite unions and arbitrary intersections. And what we see is that these sets all have a topology in which the closed sets can be defined by this rule. So the rule is that you take a set of factors that's closed under the process of taking subwords. So you take a set of words that's closed under the process of taking subwords, you call that S, and you can construct a closed set, which is all things whose factors, do I want contained or contain? I guess I want this, yeah. So yeah, it's contained. So it's the set of words whose factor set is contained in S. And what you can check is, and this is sort of just Zariski topology, is that it topological spaces. So it has a Posset structure, it has a topological structure. I should note that tot W doesn't become a topological space under this because unions of two closed sets is no longer necessarily closed. You really need the recurrence property to get this. So we can think of these as invariants. And one of the questions, and this will play a key part in our work, is these are now invariants of a word. These are some topological space or Posset, if you like, that you can attach to a word. And the question is, what are these kind of topological spaces that can arise? And you know, what are the Possets, if you like? And in particular, for us, we're going to look at things that are linear factor complexity. So I'll talk about that soon. So that's where we're going to be able to give a description of these objects. And we're going to use the Lie complexity function that we'll introduce to give a description of a word. So that's sort of the plan for the talk. But let me just recall the factor complexity function. I know most people here know it, but basically what it is it's just counting the number of factors, the number of contiguous subwords of length n. And one thing that's actually, I think, sort of a fact that's not hard, but perhaps is something that's worth keeping in mind, is that you actually get a factor complexity map from these topological spaces. So maybe I'll look at rect W to, I can think of a complexity function as a map from the natural numbers to the natural numbers. It inputs the number n, and it outputs the number of factors of length n. And this is the topological space. And n to the n, well, this is a product of copies of n. And I can use a product topology on this space as long as I put a topology on n. And I can use something called the Alexandrov topology on n, in which the infinite rays are the open sets. And with this topology, these actually become continuous functions. So this is sort of a throwaway remark, but it's actually very useful. Even though I don't think it's hard, it can sort of recover a lot of things like a strengthening of Furstenberg's theorem and things like this. So I just wanted to point that out. So what actually we can show is that if the factor complexity is big O of n, and that in particular applies to k-automatic words, then these are actually all finite sets. In fact, we're going to show the following bounds in this talk. So first, periodic set, the set of periodic factors of W is less than the limbs is less than this number kappa, which is going to be the limb sup of all differences. Now, a theorem of Cassan shows that if you have a word of linear factor complexity, its set of differences is uniformly bounded. So whatever this limb sup is, it's some number kappa less than infinity. And so that's the bound we get. You can get a slightly better bound if you assume W is recurrent, but I think it's hard to actually get bounds in the non-recurrent case. And then from there, you can show that the uniformly recurrent spectrum is bounded by this quantity, where this C is this growth constant. And then we get this really bad bound, which can probably be improved, that shows that the recurrent spectrum is at most this. And in fact, the recurrent spectrum can be pretty large. But the point is that it's finite. And I should say that there's this Morse-Hedlund dichotomy, right, that says that the factor complexity of n is either big O of 1, or it grows at least like n plus 1, which is why the Sturmian words are of such interest, right? It's sort of the first class on this sort of bad side of the dichotomy, right? These are the sort of eventually periodic words that have this property. And then there's everything else, and the sort of the Sturmian words are sort of the most basic, interesting case you'd like to understand. And then beyond Sturmian, the next class that makes sense is linear factor complexity, which includes the k-automatic words. So somehow these posets are finite, and it's an interesting question what they are for a Sturmian word or things like this. I don't know if there's been any work on it. Maybe someone like Christoph, I assume, would know something about this, but. But the important point is I want to look at is if you have k-automatic sequence, then these are sort of invariants, and there's in some sense they're proxies of the complexity of the word, and it would be interesting to understand these quantities to better understand them. And in particular, I'd like to understand the Posset of recurrent words. How complicated can it be, right? I mean, these Possets are sort of just a union of atoms, but this one, you can have all sorts of weird things that seem to occur, and it would be nice to have some characterization of what it looks like. As an example, let's look at this automatic word where you have the nth bit is 1, if n is a power of 2, and otherwise you get a 0. Then in this case, the total spectrum you can show is infinite, and the recurrent, uniformly recurrent, and the periodic spectrum are all 0 to the omega. You can sort of see that because if you truncate far enough out, you're getting really long gaps between ones. So recurrent wise, you can only, anything with 2 1s in it can't occur infinitely often. Any factor with 2 1s in it can't occur infinitely often. So if you have a recurrent factor, anything with a 1 can't occur infinitely often. Because once you have 1, you have 2 1s, and then you're bad. So the only recurrent factors are this, and they're both uniformly recurrent and periodic. And the total spectrum is infinite because you can strip off any prefix, and it will still it'll have a distinct set of factors, right? I mean, if you cut off this, you no longer have the factor 1 1. So the total spectrum doesn't need to be finite. So the main thing I want to talk about is this complexity function that Jeff and I introduced, and the paper is somewhere on the archive. And we're going to look at this function with this bound that says the periodic spectrum is at most this number kappa, and kappa, you'll recall, was the lim sup of the differences plus 1. So in this setting, we can actually phrase what the periodic spectrum is more concretely in terms of the original motivating question. It's just saying that the number of primitive factors, v, such that v to the n is a factor of w, is a finite set. And if we work up to cyclic equivalence of factors, there's at most k such words. And I'll have to say what cyclic equivalence is, but I'll say that in a bit. So now I finally gotten to the function I want to talk about, this complexity function Jeff and I introduced. And what surprised me was, Jeff has this walnut program, and it's able to compute this for a lot of automatic words. And it seems to be a very interesting function. So I'll talk more about this, but I think there are lots of nice questions about it. So we're going to introduce this function, which we'll call Lie complexity function. And I talked about being cyclically equivalent. Cyclically equivalent is just means that you can cyclically permute the word. So you can strip off a prefix and put it to the beginning, and that'll be cyclically equivalent. So for instance, here, if I take the prefix, what am I taking? I'm taking this prefix or this suffix, and I'm shifting it to the front, and I'm getting this word. So these are cyclically equivalent, but this one is not cyclically equivalent. There's no way it is, because if it were, it's cyclically equivalent to this, and there's no way of getting two B's in a row from this word. There's always a space. So they're not cyclically equivalent. So now we can define the Lie complexity function of our word. And what it is it's just the set of factors of length n such that everything that's cyclically equivalent to it is also a factor. So it's counting the number of cyclic equivalence classes with the property that every word in the cyclic in the equivalence class is a factor. And I should note that Cassin and Ficci and Sciortino and Zamboni defined something that's a little related called the cyclic complexity. And it's a little different from their definition. So in particular, ours is less than or equal to, and actually usually quite a bit less. What they look at is they look at words that where there's some cyclic fact, something in the cyclic equivalence class that's a factor. So it's a little different. So I will do an example to illustrate this complexity function right now. So let's take the two-amorphs word, and let's just look. So for words of length 1, there's really not that much to say, right? The cyclic equivalence class just consists of the word, and these are both factors. So for length 1, we get 2 factors. For length 2, notice these are the factors of length 2. This is a single equivalence class, and these both occur as factors. So we've got a 0, 1 and a 0, 1. So that's contributing 1. Since 1, 1 is a factor, that's contributing another one. And since 0, 0 is a factor, that's contributing another one. So we have 3 equivalence classes that are all inside of here. So LW of 2 is 3. And if we look at length 3 factors, well, now we've got things like 0, 0, 0, which we know never occurs in the two-amorphs word. We've got things like 1, 1, 1. We've got things like 1, 0, 0, and that's the same as this equivalence class. And let's see, are these all factors? Yes, they are, right? Here's 0, 0, 1, and you can check that 1, 0, 0 has to occur and 0, 1, 0 has to occur. So that's contributing 1 to the count. And then there's this class, and all of these are factors. So since everything in the class is a factor, this contributes 1 to the count, and this contributes 1 to the count. So we get LW of 3 is 2. And that's how you get this. And I admit I had no idea that you have expressions like this. Jeff Shallot found it on Walnut. And it's kind of an interesting story how you can even prove something like this is the case, right? Just using a computer program. If you saw Jeff's talk on using Walnut, it might give you some insight. So I'll try to talk a little bit about that. But the point is, in some sense, purely automatically, in some sense, one can prove that we have this nice formula, that the Lie complexity function only takes the values 0, 1, 2, and 3. And in fact, it's only 3 when n is 2. It's only 2 if basically you're, one of these numbers, 1, 4, or 3 times the power of 2. And then there's this. And most of the time it's 0. So most of the time there's no equivalence class, cyclic equivalence class, in which every word in the class occurs as a factor. So why is the Lie complexity function relevant? And I want to talk about its connection to our motivating problem. Notice that one way of getting a word where everything in the equivalence, cyclic equivalence class occurs as a factor, is notice that if V is a word and V squared is a factor of some word W, then everything in the cyclic equivalence class of V is also a factor of W, right? Because if I look at this A, B, A, C, and I look at something in the equivalence class like that, well, that's basically taken account of here. So in other words, this Lie complexity function is some coarse, giving some coarse description of somehow of when squares occur, right? It's giving some understanding of that. So if V is a factor where V squared is also a factor, then if we look at LWV is at least 1. So that's just this observation here. So in some sense, the Lie complexity function is bounding squares that can occur once we know it's finite. And it's certainly going to be bounding powers that occur to arbitrarily high powers. So I'm going to talk a bit about this. So here's our nice result, or I'll say, I said it's nice result. I shouldn't say that because I'm talking, but I say it's our result that the Lie complexity function always has this bound. And we're going to give a very algebraic proof, and it would be nice to have a more combinatorial proof. And the important point is that Cassin showed this very nice result, that if the Lie complexity function is big O of n, then the differences are bounded. So this shows that LW of n is uniformly bounded for words of linear factor complexity. So this is sort of the result. And this will be relevant when I talk about Jeff using walnut and things to get automaticity. So the corollaries are mainly the things I think I will actually try to prove. So the first corollary is that if we have a word of linear factor complexity, then up to cyclic equivalence, there are at most this number of primitive words that have the property that V to the n is a factor of W for every n bigger than or equal to 1. And Jeff pointed out that these were sort of proved for pure morphic words, and apparently there's some preprint maybe that's coming out that will do this for morphic words by these authors. But in particular, this applies to automatic words. So the Kluda and Strofstra result is sort of, they're dealing with morphic, and we're dealing with linear factor complexity, and there's some overlap in here. But their result doesn't cover our result. Our results don't cover their results. And the other results, and this is really where walnut can come to play, is that if W is a k-automatic word, then this LWN is actually also a k-automatic. It's a k-automatic sequence. So I just want to say for people who are more experts about this, the reason why we call this the Lie complexity function, so this proof, it's not terribly hard, but it's a little technical in that it uses Lie algebras. So what we do is we construct a graded Lie algebra, and this LWN is sort of counting some dimension of some graded Lie algebra. So that's why it's called the Lie complexity. And we can bound the dimension using this Lie algebra theory by some quantity. And then when you can compute this quantity, it just comes out right away that it's equal to this. So that's sort of how the proof goes. But like I said, it's a little technical. And, maybe some people here certainly would be able to, understand the details, but other people maybe would prefer to see a combinatorial proof. But what I'm going to do is I'm just going to make those remarks, and then I'll say, let's take this as a black box and see where we can go and get some corollaries from this. So let's see why this inequality gives us that there are at most kappa primitive words up to cyclic equivalence with this property. In particular, that's showing for an automatic word, there's only finitely many primitive words that occur to arbitrarily high powers in the automatic word. And I'll just make a remark that by definition, being cyclically equivalent is the same as having the same set of factors. So this is the same as saying periodic set of W is less than or equal to kappa. So here's the idea. The proof isn't bad at all. Suppose we had more than kappa classes in the periodic set of W. And because these are distinct, that means there's some factor in this one that's not a factor of this, and there's some factor here that's not a factor of this. And what that means basically is we can find some large integer d such that ui to the d is never a factor of uj to the omega whenever I is not equal to j. And now all we're going to do is we're going to let b be the multiple of, we're going to multiply all the lengths of these words together and then multiply by d. And then by construction, u1 to the nb over u1 is counted. It's counted by the Lie complexity function of length b. It contributes 1 to the Lie complexity because this number square appears as a factor, because u1 appears to arbitrarily high factors. And we said that once the square appears, this is contributing 1 to the count. And that's going to, and these words all have the same length. So it's contributing s to the count. And these are pairwise cyclically inequivalent. So we're getting this bound. And that's a contradiction because we picked s bigger than kappa. And we've shown that LWN is less than or equal to kappa for all n, because this kappa was the soup. So that's the idea. It's not a hard proof once you have the bound. The other corollary is slightly more work, and it uses this nice framework of Narad and Emily Charlier and Jeff Shallett that started this whole walnut software story. So we're going to look at the proof that when W is k-automatic, then LW is also k-automatic. And the relevant remark here is that we know LWN is less than or equal to this quantity kappa. So it's uniformly bounded. Because automatic words have linear factor complexity. So we're going to make use of this result of Emily and Narad and Jeff that says the following. So I've written it out. If you have a k-automatic sequence, there's some algorithm where when you have some first order expression in this theory, there's some mechanism for determining whether this is true or false, this sentence. And the important thing here is really that there's you can build an automaton that sort of recognizes tuples for which the sentence is true when you have some variables. So Jeff gave a talk on this, and maybe people saw it and have a better understanding. But just in case you don't know, I'm going to look at an example. And admittedly, I'm much less of an expert on this than Jeff and many people here. But in this example, I'm going to look at the 2 Morse sequence, which we know is 2 automatic. It's well known, of course, that it doesn't have any cubes. But I'm just going to assume we don't know that. And if we were working in this theory here, where S is now the 2 Morse word, then I can make an expression, a first order sentence that captures whether there are cubes in the 2 Morse sequence by saying, okay, there exist numbers n and I, natural numbers, so that this is equal to this, and this is equal to this. So this is a perfectly good first order sequence. First order sentence. Now, the only thing to remark is, notice we've got plus, we're not allowed to multiply. So things like 2i and 3i shouldn't be allowed, but of course, it's not a problem for us because 2i is just I plus I, and 3i is I plus I plus I. It would be a problem if we had something like I squared, because I'm not allowed to use an ellipsis or something like this, but I can, this is certainly fine. So, so what the theorem says is, even though we already know the 2 or more word contains no cubes, it says if we didn't know that and we wanted to check, we could plug this expression into Walnut and let Walnut tell us the answer is no, that this is this sentence is false and the 2 or more word is cube free. But what's nice is it says more. It says, let's say that I have now just a general automatic word that I'm interested in. So maybe it's not the 2 or more word, and maybe it does have some cubes. Then I can ask, what is the set of ni where we get a cubic factor? So basically it's saying, what is the set of n and I, so that I have a cube like this, where it's v cubed with v of length I occurring at position n. And what Walnut does is it builds an automaton that accepts these pairs ni. So it gives a regular language that shows the positions n and the lengths I, where I have a cube of a length I factor occurring at position n. So that's what's sort of relevant here for us. Now, like I said, we need to know the fact that LW of n is uniformly bounded for this to work. But notice that if we look at the expression LW of n is at least I, that's expressible in the first order factors. So first of all, saying that you have factors with the property that all cyclic permutations are again factors, that's expressible within the first order language, right? It's just saying, you're looking at Wn, n plus 1, n plus I, and you look at all shifts for each j, from 0 to I or whatever. You want to know if there's some other natural number where, the shift equals, well, I'm not doing a very good job of expressing that, but if I wanted to say, okay, if ABA is a factor, I can check that, and I can check BA, and for each word of length I, there's only I cyclic things to check, and I can just make some expression that says, okay, these are all factors. So we can decide when 2 length n factors are cyclically equivalent. And so we can determine whether there are at least I cyclically inequivalent factors for which every cyclic permutation is a factor, right? So at least I is saying, okay, there exists factors 1, 2 to I, such that everything in the class is a factor in the cyclic class. That doesn't tell us that there are like 100 factors, right? I could have I equals 3 and maybe there's actually 100, but we see we can at least express this. And so what we were saying before is we can actually accept the set of natural numbers where LW of n is bigger than or equal to I. So this is k automatic for every I. And since LW of n is uniformly bounded, we then see that it's an automatic function. So that's sort of what's relevant here. So I already showed the 2 or more example that Jeff computed using the Walnut. I have no idea how to use Walnut. I saw Jeff give the talk, of course, but I don't even know how to use GitHub, unfortunately, or whatever you use. So I should probably learn, but I don't think I have to learn because Jeff is he's so much better than I am at doing anything like this. And at translating things into first order sentences. So I'll give some more examples. So here's the Cantor sequence. So this is 3 automatic. It's the fixed point of this morphism that starts with 1. And again, interesting is that you only get 3 values, again, 3, 2, and 1. And you only get the value 3 when n equals 4. And you only get the value 2 when you're in this quantity, in this set. So what seems to be happening in a lot of these examples for some reason is you get some value that occurs almost always, and then you get these sparse sets where you get these anomalies occurring. And we haven't quite, I don't know if Jeff or I have really understood why that seemed to be the case for the examples. Maybe it was just a function of the examples that we looked at, but it does seem to be the case that there's sort of a generic value, if you will, of the Lie complexity function, and then sort of other values that jump on sparse sets. So you saw that with the two amorphs, where generically, and I'm using generically in a sort of imprecise way, you get 0, and then there were these sort of sparse sets of powers of 2 and stuff where you got other values, bigger values. And here's another example of that philosophy that seems to come into play. If we take the Fibonacci word, this is not an automatic word. It's just a morphic word. So it's sending 0 to 0, 1 and 1 to 0. Then what you can compute is that it takes 3 values. And again, it's only 1 on this very sparse set of Fibonacci numbers and a sum of 2 Fibonacci numbers. And then it's 2 for just a finite set of values. And then it's 0 otherwise. And I don't have a good understanding of how Jeff was able to compute this, but I guess there's some way of handling morphic sequences embedded in Walnut. But this is sort of another illustration of that, this question. And another example, Tribonacci word. So here, again, it's this morphic word. And so we've got the Tribonacci sequence, which is defined analogously to the Fibonacci sequence. And if you look at the Tribonacci word and its Lie complexity function, again, it's got this sort of sparse, this union of sparse sets where it takes the value 1 and it takes values bigger than 1 only on a finite set. And then it's sort of 0 most of the time. So there is a question. It seems like the smallest value is smallest value of LWN. Does it hold? Is the set of n, let's call the set of the smallest value min, is this almost all of n? Whereby almost, I mean its complement is sparse. Its complement is polylogarithmically, its counting function is polylogarithmically bounded. So it's sort of, a finite union of something like, sparse languages. Maybe that's not true. I don't know, but it just seems to always be the case. I'll give one example. Narad knows Blake Medill, who was an undergrad at Winnipeg, and he came to Waterloo and he did a PhD with me. And one of the things we worked on was we were working on this this problem about nilpotent, graded nilpotent rings. And we constructed some example that people were asking about. And we did it via, automatic words. And this word we gave was sort of unnecessarily complicated. We gave it on such a big alphabet because we wanted the word to have some other properties as well, because that's what was being asked for. But one of the things we showed was that that this function has LW of n is always 0 for n bigger than or equal to 2. So it can be 0 once you get to a certain point. So what this is saying is it's giving a word in which every factor of length n has, every factor of length at least 2 has some cyclic conjugate that's not a factor. And I should make the remark that this was later improved to a 5-letter alphabet. And even just this question of, is LW of n 0 for n bigger than or equal to I, has been studied on other alphabets as well. So, so there is some sort of, there's been some work in the past of looking at LW of n being 0. Seems to be an interesting property. And if you were to translate what this says in terms of some Lie algebra, it's saying that, some Lie algebra we get is finite dimensional that we construct. So I'm almost ready to end the talk, but I want to sort of finish up and mention one thing. Throughout what we did, we were always assuming that the subword complexity function is linearly bounded. And in that case, we showed that LWN has linearly bounded factor complexity. And I should point out that, you know, using that, you get that this was finite, and you can use that to show that rec W is finite. So, so this is sort of the first step, and then you can use that to show all these quantities are finite. But it doesn't really answer the question of what happens beyond linear factor complexity. So you could ask, what happens if you increase the growth a little, like maybe you look at log n, log n. So what if the factor complexity is big O of n log n, or something just a little faster than linear? Do we still get finiteness? And it actually fails no matter how close to linear you get, as long as you exceed linear. So if you take whatever function you like and just make sure it tends to infinity, but it can tend to infinity as slowly as you like. So you could take, you know, log n, or, you know, inverse Ackermann function, or whatever you'd like. Take any function that's just going to 0 to infinity very slowly. Then there's a right infinite word whose complexity factor function is bounded by NFN, which has the property that it has infinitely many distinct primitive factors, such that y to the n occurs as a factor of w for every n. So in particular, from the proof we gave earlier on, that shows that the Lie complexity function is unbounded, that the lim sup is infinite. So one last question is, we showed that this periodic set was finite, and you can use that to show that the recurrent spectrum is finite, and it's some nice partially ordered set. And one question I'm interested in is, you know, you take some class of words of linear factor complexity, maybe Sturmian words, it's not so interesting, actually. I mean, for Sturmian words, you always get a singleton. So for Sturmian words, it's easy. It's always a singleton. So that's not hard. But for automatic words, it seems you can get somewhat complicated posets. And the question is, can we somehow characterize the posets, which can be realized as rec W, with W a k-automatic word? So I don't know the answer. So if someone does know some way of characterizing, that would be interesting, but it'd be sort of an interesting invariant that I don't think has been looked at. So anyway, that's the talk. So thank you, and I'll stop there.
Oh, thanks a lot, Jason. Does anyone have any questions for Jason? Yeah, Gabriele.
Hello,
Hi.
Jason. I'm Gabriele Fici.
Hi.
Just a remark. When we wrote the paper about cyclic complexity,
Yeah.
we observed that as soon as there is the cyclic complexity takes value 1, then the word must be periodic. So what happens, in fact, is that in order to have more cyclic conjugacy classes, you must have special factors. So in some sense, I'm not surprised about the result of your theorem, because in order to have new Lie complexity classes, you need special factors, and the number of, let's say, right special factors is given by the first difference of the factor complexity. So this could be a strategy for having a combinatorial proof of your theorem.
I see. Yeah, that would be nice to have this to have a combinatorial proof. Yeah, because it's not so straightforward to translate the algebra. I mean, I thought about trying to translate it. It's not so straightforward. So maybe different, like you say, it's a different strategy with the special factors. Because you're right, you want to see somehow the difference in a natural way. And so yes, I think maybe you're right.
Christoph?
Yes, hello.
Hi.
Thank you, Jason, for this nice talk. And they are very nice algebraic and topologic concepts. which I like, and I think they are very deep. I wondered, you just said that in the Sturmian case, it's a singleton, the periodic set.
Yeah.
You mean
The periodic set is empty. Sorry, the periodic set is empty.
Ah.
And but the recurrent spectrum is a singleton.
yes, it reminds me that something with a result of Mignosi, I think, which says that arbitrary powers occur only when if and only if the how it's the quotient partiel, the partial quotients are unbounded.
So maybe I'm.
But I'm not sure that it's for the same word. So you say it's empty anyway.
So you're right. So I guess the periodic maybe the Posset structure is more complicated than I'm thinking. So, so I think the Sturmian word, yeah, you're right. Maybe the Posset looks like it has something at the bottom and then some periodic things at the top. So maybe it has, height too. Maybe there's this and then some periodic stuff, and it has. Yeah. So I guess it is sort of an interesting question then about the.
No, I think Christophe is right. I think the result of Mignosi, there is a result of Mignosi that says for any given factor,
yeah,
it does not occur with, no factor occurs to arbitrarily large exponent.
Oh, no factor occurs to
no individual factor, right? So you can get larger and large, you can get arbitrarily large exponents, but you have to take different factors.
So then that says that the periodic spectrum is empty.
Yeah.
And the recurrent spectrum should be a singleton, I guess.
I think so.
Yeah. Okay. Oh, that's nice.
And now I have another question or comment, is that you just, it's for Sturmian words, sequences, infinite words, I mean, the Lie complexity is, did you compute it? It seemed to me I guessed it's only 0 or 1, but your example of Fibonacci just is of course, it's not true what I say, and I thought that perhaps it's 0 in general, and 1 only when the length of the length is denominator of the continued fraction. But it's not true after your example you showed with Fibonacci. So my guess is false.
Yes, you're right. So we show for Sturmian, you always get the values 0, 1, or 2.
2.
You can take the value 2, but it seems that in practice, the value 2 only ever occurs finitely often. So for the Fibonacci word, it only occurs when n is 1 and 2. I don't know if now there's this software for dealing with Sturmian words, so maybe it can tell us this, but yeah, in general for Sturmian words, I think it should be 0 almost always, and then it should be either 1 or 2, and maybe 2 on a finite set and 1 on something dealing with continued fractions or something, but I don't know quite how to express it, because with 1, you're right, you get for n equals Fibonacci, you get 1, but you also get these fk plus fk minus 3 for some
reason. Yes, it's very strange. I mean,
I think Gabriele wanted to say something again.
Sorry, it's about Christophe's remark that actually I had the same remark. When I saw the example about Fibonacci, I was a bit puzzled because what happens is that if you have a factor of length n and you want that all the conjugates are factors and this factor is primitive, then you must have n distinct factors. So since there are n plus 1 factors of length n in a Sturmian word, this means that you have n factors that are conjugate and one that is in another conjugacy class. And this happens precisely for Christoffel factors. So whose length is the length of a bispecial factor plus 2.
I agree. It's the same thing as looking for which are the Christoffel words which are factor of
But this is for primitive, proof
Yeah,
for
so
primitive.
Primitive, yes. Non-primitive, I don't know.
So probably these are somehow squares or something like this, maybe.
Mhm. So I'm a little bit worried about the formula Fn plus Fn minus 3 of, anyway, well,
Well,
it should
I
be.
mean, it seemed to be done on the computer, so it's, I mean, I think it's been checked. Yeah, I have some more insight into that, but
And maybe you could put the formula up again and see.
oh yeah, maybe I have to share screen again. Let me just share content. Let's see. There we go. Share. Yeah, so that's the formula. And I mean, Jeff used his sort of the walnut magic to find this.
Yeah. I mean, I'm fairly confident it's correct, but I certainly can double check it.
Mhm. Yes. Do you know, it reminds what you do, you could take, instead of infinite words, you could take factorial languages, language which are closed under taking factors. Huh? And it reminds, it looks, do you know this notion of zeta function of a language, which seems to be connected to this, because it's a notion we introduced with Erstel 30 years ago. You count the number of, oh, it's a little bit difficult to explain, but it has to do with the powers of words and conjugacy classes and language.
Huh. Interesting. No, I've never seen this. That sounds very interesting.
So anyway, I have no more question. I just thank you for your talk. It's very nice talk.
Oh, thank you, Christian.
Did anyone else have any questions?
I'll just say one quick thing, which is, for example, for in this case of Fibonacci word for n is 16, there are, if I don't mistake, 2 different cyclic classes, each of size 8. So it's possible that perhaps it got in copying, perhaps it got copied wrong or something like this.
Maybe I'll ask one thing before we go. So I think it makes sense to me where you got those sporadic positive values for like 2A Morse.
Yeah.
Because the squares in the 2A Morse sequence, their lengths are precisely powers of 2 and 3 times powers of 2. Right, so you'll get those positive values whenever you have a square, and it's known what the lengths of those squares are. So that sort of makes sense to me. And what I was wondering was, like, can you construct a word where you have positive values infinitely often that don't come from squares? Like, can you construct a square-free word on 3 letters, let's say?
Yeah.
Where this function has positive values infinitely often?
That's a very nice question. So I don't know the answer. I mean, the sort of naive way we thought of, giving some contribution is by putting a square in, right? So my guess is that maybe there is some example, but you're right. It would be a bit of work, and it would be very interesting if you were right that or if it ended up being true that somehow you need to have squares to get something positive.
I mean, you can do it on a large alphabet, right? You could, if you picked a very large alphabet, you could just use the extra letters to build in, to just chuck in some cyclic.
So, I mean, for a general word, you can certainly do it. For automatic, yeah, I mean, it's on 3 letters. Maybe it's an interesting question. I'm not sure what my guess is maybe there is some example where you can do it. Not Sturmian was, I forgot. The non-primitive conjugacy classes. Okay, that makes sense then. Yeah, I should say, we had this example with Blake on the 5-letter alphabet. And I think if you look at this, you can sort of see that it can't, well, it's sort of designed in a way that I think, okay, so this is 0 for every n in its square. Yeah, I think that's an interesting question. I mean, there's some connection with squares and being positive, but it's like you said, it's just a one-way implication. So yeah, the question of what happens in general, I'm not sure. Yeah, that's very nice.
All right. Well,
just one more thing. I
Yeah.
just checked it for some values, and I think our formula there was correct for Fibonacci. So
yeah, Christoph also had a comment in the chat.
okay, yeah.
That explains.
Okay, good.
What's going on. Anything else from anyone? If not, thank you all very much for participating in the seminar. That's the last one for the summer, and I guess we'll be in touch again for when the seminar resumes again. All right, so enjoy your month of August.
Thanks,
And,
Narad, for being such a great host.
Oh, thanks, Jeff, and thanks to all of my co-organizers for
Yeah, thank you.
all of their work.
It's been a very nice seminar. Thanks.
All right, thanks everyone. I will see you all. Bye-bye.
Bye.